Hello again. In the first part of this introduction, we considered the tank with a heat exchanger, and we control the valve here, which allows more or less steam so that the temperature of the tank is maintained at certain value. We tried first to implement the expert system using crisp membership function, and one drawback of such a scheme was that similar temperatures, I think the case we considered was 24.9 and 25.1, very similar temperatures. Probably the human operator would take very similar action, or actually not be able to distinguish between the two. But our controller using crisp membership functions gave us two different actions. To overcome this difficulty, we used the fuzzy membership functions, and we use the simple form of fuzzy membership functions, the triangular forms here. And with this fuzzy membership function, we considered the two cases of the purple and the red temperatures, which are very similar, and we found that the action we get is similar, 2.51 and 2.49. If you look at the part 1 of the presentation, the crisp membership functions gave us two different actions, +3 and +2. So we can see the advantage of implementing the control using fuzzy membership functions. So far, we have considered the operator's action assuming the inlet temperature, i.e. that's the temperature of the fluid coming into the tank, remains the same. In reality, the temperature would vary, and so would the action of the operator. For example, if normally the temperature was 15 degrees, and today the temperature is coming in at higher value, 25 degrees, then the operator would adjust his or her actions, will allow less steam than the previous case of 15 degrees. So his action or her action will be modified to, if it's okay, leave the valve as it is. If it's a small negative, it's plus 0.5, open the valve 0.5 increment compared with one full increment in the previous case when the temperature was 15. The opposite occurs if the temperature comes in at lower value. So the temperature of the fluid coming into the tank today is 5. We'll need to allow more steam. So the operator would change their action, and here they increased the opening of the valves. Compare this with the original case when we assumed 15, here with +1, +2, +3. Now, when the temperature, inlet temperature, is a bit higher, we need less steam. When it's a bit lower than 15, we add more steam. Now we have two variables, and we will need to combine the two variables in a two-dimensional table. When we consider the implementation using crisp membership functions, we can divide our inlet range of temperature as shown here, and also the output temperature as measured. So to illustrate how this two-dimensional table works, if the inlet temperature today is 5 degrees and the measured temperature of the tank is 30. So that's 30 and 5. So the action will be to open the valve 3 increment or 3 turns. If the temperature into the tank is 25 and the measured temperature is still 30, the action will be +1. But of course, here we're still using crisp membership functions, and we know the problem with the crisp membership functions is that we are going to get widely different actions for similar conditions. Implementing this in fuzzy, we use triangular membership functions. So this is what we used before when we had only the output temperature as the measured quantity. Now we have the inlet temperature, and we divided the range into cold, normal, and hot. Just to explain, the center of medium negative is there. It's the 30 degrees is 100% in the medium negative. Similarly, OK is exactly 50. Medium positive is exactly 70. Similarly with the hot, the center of the hot will be 25. The center of the normal is 15. That's what normally the temperature is coming to the tank at. And the cold is 5. Difficulty here is, if you remember the previous case when we only had this row, we didn't have this part at all. So what we did, we looked at a temperature. If a temperature, for example, like this one here, this is 25 degrees. 25 degrees will be 50% in medium negative and 50% in large negative. So it will be 0.5 multiplied by this, 0.5 multiplied by this, and that will give us the action to take by how much we open the valve or close it if the temperature was high. The difficulty now is we have this inlet temperature. So we have values, and how can we combine the values coming from the two membership functions to yield one action, which is going to be the control action going to the valve. This is illustrated in the following. In this case, what should the control action be? So we're considering here just a part. I didn't want the full table and the full membership functions. I'm assuming a temperature at 64. If the temperature at 64, it's somewhere here. This obviously belongs to medium positive and also belongs that much into small positive. So I need this section of my rule base. And we're assuming that the inlet temperature is 12 degrees. 12 degrees belongs to cold, and 12 degrees belongs also that much to normal. So it will need the cold and normal. So I need this part of my table. So for this condition, the part of the table that I need is these two columns, these two rows, so it will end up with this. Actually, if I delete this, you will find that it's in the presentation. So I'm showing here the membership values. It's 64 degrees, belongs 0.4 in medium positive, 0.6 in small positive. Similarly, inlet temperature of 12 degrees belongs 0.3 in cold and 0.7 in normal. And that's the effective part of the table I need. I'll take that down there. Then I will take also these values. I'll put them in my table. So I get these action values. The small positive here gives me 0.6. That's the membership of the small positive. And here the 0.3 is the membership in the cold. So now I have in each square, I have two values, a membership percentage of the output and the membership percentage of the inlet temperature. And there is only one action. How can I combine these to get one action? There are many methods. And the method we are going to illustrate here is the intersection fuzzy and, also known as the minimum weight. What is the minimum weight? You look at each square, see which value is the smallest, and you take it. For example, in this case here, if you look at this square, which value is the smallest is the 0.3. So we delete the 0.6 here, we delete the 0.4. And our action will be a combination of what's left and the rule base as indicated in each square. How can we arrive at this value? The control action becomes, and as shown here. I will summarize in a minute exactly what we have done, but this is an illustration of how we obtained the control action when you only had one variable, and now how we can combine two variables in 2D table and get one action that goes to the control, to control the valve in this case. To summarize, fuzzification. What do we mean by fuzzification? Fuzzification, we mean any temperature will belong to some degree on one category and to the other degree on another category. So in this process, each value of temperature, for example, we used 64 degrees in the previous slide. 64, we found that it belongs 60% in small positive and 40% in the medium positive. So fuzzification is the process where the crisp quantities are controlled to fuzzy. Here, fuzzification was done by assigning membership values for a given crisp quantity, inlet and outlet temperature. So more about fuzzification. Membership function. How can I decide the membership functions? We decided on them here by intuition. That means we knew something. You cannot decide on the membership functions if you don't know what is the variable you are controlling. For example, here I consider a case of a speed of a motor. The speed of a motor, if it's, say, an induction or a DC motor running at line frequency, if it's an induction motor, then I will define the range as low, medium, and high. Well, I decided that something like 12,500 is medium, something above 2,000 is high, something below 500 is slow. How did I decide that? I decided that by knowing what a motor is and what speed is. If I didn't know what speed is, how can I decide this? If I didn't know what type of motor, I didn't know what range of the motor speed is, I would not be able to divide the range. Once I divide the range into like this, I can say a temperature of 1,000 will belong to medium and also will belong to low, and so on. So to summarize, the speed range is split, but we could not have been able to fuzzify any value of a speed like 1,000 unless we knew the nature of the variable we are controlling, the speed, and also how that motor operates. We use triangular functions, membership functions, but other do exist and are indeed used. The second element of the process, the rule base, the knowledge-based lookup table. Where did we get that from? From the operators or the experienced engineers who know the process very well. Third step was the inference mechanism, and we implemented it here with if-then statements. The example we just considered, when the temperature was 64 degrees and the inlet temperature was 16 or something like that, these are the if-then. If the temperature is a small positive and Ti is cold, if it's small positive, we are here. If it's cold, we are there. So it concerns this square. This square, we know that the action will be minus 0.5. Yes, value is minus 0.5. And which one of the membership functions values we're going to use? We have 0.6 and 0.3. We use the minimum. This is in the method we employed here. Similarly, you can look at the rest of the if-then statement. The last step is defuzzification. How to combine all these if-then statement outputs to get an action, a crisp value, specified value that is applied to your controller. And here we applied the center of gravity defuzzification method. However, there are many other methods. This method enabled us to obtain a crisp value from multiplication of the minimum of the number of, in this case, 2 membership values with the action, as illustrated here, divided by the sum of the membership functions. Next part, we're going to look at how is fuzzy control is related to conventional control and how can we implement fuzzy control using MATLAB and Simulink.